Hi, and welcome everybody for the Aerial Robotics Community Group meeting. We have a presentation meeting today on May 22nd, 2024. And we'll have a nice presentation from Matej Karasek from Flapper Drones. But before we dig into that, we have a couple of announcements first that we would like to share with you all. First of all, the ROSCON call for talks deadline is about 2 weeks away. It's the 3rd of June. So if you are planning to go to ROSCON this year, and if you want to, talk about the cool project that you're working on, make sure to not wait until the last moment. And also tomorrow, the ROS distro Jessie will be released. I've been helping out with testing it, and it looks really cool so far. But if you're a package maintainer and you are planning to also release a Jessie, a ROS Jessie Jellicoe version of that, then they're asking if you want to write your Jessie jives for that. So, and perhaps the biggest announcement right now, we have a website now called the Aerial Robotics Landscape website, and it's ready to be shared and appended and to be added on. So it's a website that you can actually that's providing an overview of anything related to aerial robotics. So in terms of platforms, education, tutorials. I don't think the Flapper drone is there. Should definitely be there.
But I saw some helicopters there.
Yes, absolutely. So this is the this is URL. I think Ramon could share it on the chat. So you can take a look, and if you feel that anything is missing, please make a pull request and add that information. Or if you think we should add a full new page, also let us know any issues. That is pretty big. So also a big thank you for everybody from the Aerial Robotics Community Group that has been helping out so far of making this initial collection happen, so we can even make it better as time goes on. All right, so now we have a presentation by Matej, and he's going to talk about the Flapper drone. So I will stop sharing my slides, and then Matej, you can share yours.
Okay, let me see if I find the right window. That's always tricky. Okay, let me just, there we go. Okay, you should be seeing it now.
Yeah, I can see it.
Perfect. Yeah. Okay, hi everyone. Thanks a lot for inviting me to give a talk here. I must say I'm quite new to ROS, but as I'll show you in a bit, our Flapper drones are actually to some extent supported in ROS. So so as the name suggests, Flapper drones are quite unconventional drones. They use wings instead of propellers. And I'll give you a little bit of an introduction why we are doing this and what we do. Very shortly about me. So by education, I'm a mechanical engineer, but I then worked for 10 years in academia, and there I really developed insect or hummingbird-inspired robots. First in Belgium at Université Libre de Bruxelles, and then in Delft, where I was a postdoc, and that's also where I met Kimberly, who invited me. She was a PhD there. And during this time, we developed a robot which became basically the foundation of the spin-off Flapper drones. So Flapper drones, as I mentioned, is a spin-off of Delft University of Technology. We're still a startup company, very small. The first steps were taken in 2019, but since 2022, we are in Czechia, which is my home country. It doesn't really matter that much because most of our customers are across the globe, so it doesn't really matter where we are located. And so what we do, well, mainly we develop and manufacture insect-inspired flapping wing drones. they're insect inspired, but it doesn't mean that the size is at insect scale. They're actually bigger, as I will show you. At a smaller, let's say, scale, we also do shows and entertainment gigs with these drones. And we also do some consultancy work on flapping wing actuation, drone design, etc. We are a very small team because actually the whole company is funded just by our sales and services. So we don't have any investment money. So we are 2 employees, and we work a lot with external collaborators when we need to, like improve certain aspects of the drone manufacturing processes. And we have advisors, Rick, who is a co-founder of the company, and then Guido, who is a professor at TU Delft. So with him, we consult things related to research and new things there. Because these drones are quite unusual, I think I'll talk very briefly about actually how natural flyers fly and what we actually learn from them to design robots with wings. So if we look into nature, every animal that can fly has wings, but bigger birds, they flap their wings up and down. And they basically propel themselves with the wings, but then the wing generates lift because of the airflow around them as they move forward. But if they want to slow down, they have to start flapping more horizontally. But for the large animals, this costs too much energy, so they cannot really sustain hovering flight for longer periods of time. While small animals like hummingbirds and insects, they are masters at this, and they can do that for minutes. And the reason is scaling. So at small scales, there is a little tornado-like structure next to the wing, a vortex that improves the lift generation. But this vortex will not be stable for the bigger flyers. So hovering flight is only possible at small scales, and this is also a limitation for us when we design drones with flapping wings. Now, for a drone, it's very nice that if it can do vertical takeoff and if it can hover, and this is why we take the inspiration from these small animals. Now, okay, the wings, they give you thrust or lift, but then how do you control flight, especially when you're an insect without any tail? Well, then you have to adjust the motion of those individual wings and create some differences in the thrust of the individual wings to generate roll, pitch, and yaw moments. So this is an example how you can generate roll. You can increase the amplitude of one of the wings, or you can just change the angle of attack of the wing throughout the wing beat. Then you're going to roll. To fly sideways, well, insects do that similar to helicopters. They just tilt to the direction where they want to fly, and then they fly. Similarly, to generate pitch, you would move your wings, for example, backwards to generate the thrust more behind your center of mass. And to generate yaw, you have to create some difference in the drag forces of the individual wings. And you can do that, for example, by adjusting the angle of attack on one of the wings in half of the wing beat, for example. And so as engineers designing these robots, we're looking for solutions that are simple, lightweight, and that require minimum of actuators. And what is important is that all these 3 control moments that we need to generate, it needs to be decoupled. So you have to be able to generate all of them at the same time if needed. We're not the only ones working on these robots. There are many, mostly university groups that do that. You can see some overview on this not very nice slide. But you can really go to insect scales, as you can see on the left side of the slide, but then it is very hard to fly freely. It's hard to integrate a power supply. So all of these actually, they either have tethers that provide power, or they use some tricks like high intensity light and a small photovoltaic array to transfer the energy to the drone. But it's still nice that they can demonstrate at really insect scales that flight is possible there, controlled flight. But yeah, if you want free-flying robots, then the smallest ones are in the range of 10-20 grams and a wingspan starting at around 15 centimeters and more. But these are, again, all prototypes. So actually, what we do at Flapper Drones, we're the only company that turned this into a product. But we started also at university. So this is the late prototype that we made in 2018 that we called the Delphi Nimble. The wingspan of 33 centimeters, mass of 29 grams, but yeah, it could hover for over 5 minutes. So at that time, this was state of the art, not because of the flight time. There were slightly better flyers, but because of the agility. So it could hover, turn around, but also do very agile maneuvers like these rolls and flips. And yeah, at this point we were okay. So we now have a robot that could actually do something that has some advantages over propeller-based robots. And at the same time, we got approached by people from the entertainment industry asking us if we could do a show with robotic birds. And this is what actually started the company. This was our initial vision, creating a show with flying birds, but it could also be flying butterflies, flying fairies that would fly in a swarm, in creating formations together with music and light. Many things have changed since then, but basically this use case defined to some extent the size of our current models, but also the kind of requirements we had on them and the choices we made. Here, this is finally our current product. So it's called the Flapper Nimble Plus. We sell it as a development platform. I would normally demonstrate it, but since this is an online lecture, I'm going to play a video instead. So as you can see, it can, it flies by flapping its wings. It can do vertical takeoff, it can hover, and it can fly in virtually any direction. So you can fly forward, you can turn, and later on you will see that it can also change directions and stop and start flying, and can do it very quickly. It can do almost horizontal flight when you go at full speed. Now the wingspan is about 49 centimeters. I actually have one with me here, so you can see the size. So it's quite large, but for this size, it's quite lightweight. So only about 100 grams. I'll talk a little bit about how it works on the next slide. But for the flight time, with the standard battery, it's about 8 minutes. But if you don't need to carry anything, you can use all the payload capacity for a bigger battery. So with a bigger battery, you can do up to 15 minutes. And so this is actually the first tailless flapping wing drone, which means the first insect-like or hummingbird-like drone that you can actually buy. Now, so how it works. So inside, we have 4 actuators. And there are 2 brushless motors that are driving the wings. And each of the wing pairs, the left pair and the right pair, they are independent. So we can drive them at different frequencies. So this is how we do rolling. To control pitch, we can actually adjust the angle between the 2 wing pairs. And finally, we have an actuator that deflects the roots of the wings. And this is how we get yaw moment. So very simple mechanisms, but very effective. And as you could see, the drone flies really like a hummingbird, like an insect. So yeah, you're probably curious, okay, how is it controlled? So actually, the very first prototypes were using paparazzi-based autopilot. But since these were custom made because we needed a very lightweight one, we were then looking further. And we landed on the hardware from BitCraze. So in the Nimble Plus, we're using the CrazyFly Bolt, which is a pretty standard in terms of hardware. So STM32F4, you might be familiar with that. Pretty standard IMU. But the reason why we chose it was not because Kimberly works there, but because the Crazy Fly ecosystem supports all sorts of different positioning systems, indoor positioning systems, which was our original use case. But you also get the open source firmware. We actually had to push quite a lot of changes in there to enable platforms which are, not quadcopters, because originally this software was written for quadcopters, and many things were hard-coded there. So we have 4 actuators, but 2 of those are servos. As you can imagine, there were quite some changes needed. And you can do high-level control with Python API, also from the Crazy Fly team. As I explained, I don't use ROS myself, but actually our products are, to some extent, supported in the Crazy Swarm 2 project. Because the Python API is the same for the Crazy Flies or for the flappers, and basically anything you code for one of the platforms is very easily portable to the other one. And the same holds true for the Skybrush, which is an open source drone show software developed in Hungary by the team of around Gabor. I forgot his surname, sorry about that. Another nice thing is we have a lot of interfaces available for add-on sensors. I2C, SPI, UART, GPIO, whatever you need to connect, you should be able to. We even integrated interface for RGB and addressable LEDs. So if you want to have some nice lights on the drone, that is easily possible. And data logging is also integrated. Unlike on the standard Crazy Flies, though that might change with the newest one, as far as I know. Now, you can also use, if you don't want to integrate your own sensor, you can also use the DEX originally designed for Crazy Flies, which many of them will just, connect to our flight controller as is. For some, you might need external extension cables, like you can see here, because they need to be placed on the top or at the bottom of the drone. And finally, the drone supports various positioning systems, which I show on the next slide. So this is actually, again, some figures from Bitcraze. The Crazy Fly ecosystem supports various motion capture systems, Vicon, OptiTrack, and as well as others. It's also very easy to fly the flapper using the Lighthouse system, so base stations for VR made by HTC or Steam now. And finally, you have the option to use ultra-wideband radio beacons. This is something that is less accurate, but the hardware is supported, and you can get reasonable flights also with that. To program the drone, if you have a positioning system, it's very simple. Here is an example. If you want to fly one drone, you just write commands like takeoff. You say the height and the takeoff time. You have commands to go to XYZ and to land. And it's equally easy to fly multiple drones. Of course, you don't write just this code snippet. There is some code around that, but it's still very easy and intuitive. So with this, you can do already quite some nice shows. Of course, if it's not really scalable, so if you want to fly more drones, then you might want to use the Skybrush software, for example, or the Crazy Swarm project. I'll mute it so that you can hear me better. But yeah, here we use the Lighthouse system, again, from Bitcraze. And as you can see, we have a very good control of the position of the drones. We can change the light. So yeah, for entertainment, this is a nice development platform. Okay, I'll talk a little bit about the power consumption of these drones, because since they are not very common, many people might think, okay, maybe they consume much more power than conventional drones. This is actually a study made at TU Delft with one of our, like 3 preliminary, let's say, pre-release products. They fly autonomously in OptiTrack in front of a fan array. Yeah, this is actually the power consumption measured at different wind speeds. On the right for the flapper drone, and on the left for a crazy fly. And well, there are 2 things you can notice. First, the power efficiency is actually better for the flapper drone. It's about 6-7 grams per watt when you hover, and it's even better at 2.7 meters per second, where it's around 8 grams per watt. So only about 80% of hovering. So there's this trend up to a certain speed, your power requirements are actually lower as you fly faster. So that's a nice thing of flapping wings. You get more efficiency when you fly forward. And this is not a fair comparison because we're comparing a platform which is lighter and with brushed motors. But still, you can see that there the power efficiency is about 4.5 grams per watt. So, like about 70% of the flapper drone. Of course, with rotors and motors, the bigger they are, the more efficient they are. But for a 100-gram drone, you would get similar numbers to what we get with the wings. So it's actually pretty good. And yeah, if you want to fly with some extra payload, or if you want to integrate a bigger battery, we also did some tests. Here you can see the mass breakdown. Just yeah, so if a 30-gram payload, which is the maximum we recommend, would represent about 20% of the total mass. And here on the right, the yellow zone shows basically the top graph is power efficiency, so thrust to power. I think the units are the other way around, so this should be grams per watt, gram force per watt. And at the bottom we have thrust, and the yellow zone shows basically the bottom is the unloaded case and the top is the full payload case. As you can see, the efficiency is pretty much constant in this range, and it remains around 6.5 grams per watt, which is nice. And this also means if you want long flight times, you can use this payload for a bigger battery, and as I explained, you can get up to 15 minutes. So the applications of these drones that we sell are mainly in R&D. Because of the open source firmware, because it's easily programmable, because of the compatibility with additional sensors, positioning systems, and also because it's the first drone of this type. We sell a lot of these to universities and also companies that want to try out their sensors on these platforms, for example. But now with, let's say, the technology a bit more mature, we're also looking into drone shows and entertainment, which was our original idea. The advantages there, and I'll talk about it a bit later as well, is they're interesting visually. You don't need, like 100 drones to create an image of a butterfly, because you can actually fly a real or a robotic butterfly. But they're also safe, as I'll show you, because of the soft wings. And yeah, we can operate them autonomously indoors. And finally, STEM education is one of the applications, because you can use this not only to teach about robotics, programming, but also about biology and about mechanical design. Yeah, in research, this has already been used in a couple of high-level publications. So there is a science paper where we used one of the first prototypes to model flight of fruit flies, and you can also use the platform to test algorithms that are bioinspired. For example, the team of TU Delft did this paper on attitude estimation from optic flow, and basically they showed flapping wings actually have advantages because when you hover and don't move, it's an unobservable state for them. So you have to actually tilt a little bit the robot to get to an observable state. But with a flapping wing, you're always oscillating a bit, so you're all the time in an observable state. We also do some small entertainment gigs with these. Because they're safe, we can fly them really close to people. So we did a lot of things together with dancers. And you can actually, put additional, things to decorate the drones to make them more visually interesting. Again, you don't need that many units as with conventional drones to create a nice show. And the sound is also, less disturbing. Actually, you can hear the flapping. You can even transport objects. And here just some slides showing the various appearances these can have. And yeah, finally, we can even change the wing shapes and print on those. For performance, we actually optimize the wing shape that is at the bottom left. But if you don't mind sacrificing a little bit of flight time, you can really go creative even with the wing shapes. So okay, that was for entertainment, but why else would you like to use flapping wing drones? I already hinted that they are safe. They're safe because they have soft wings. The wing is moving back and forth, so whenever you hit something, the wing has just stopped. It's not like a rotor, which has a lot of energy stored in it, and whenever you hit an obstacle, all this energy has to get dissipated. And at the same time, a wing can tolerate collisions much better because it will bounce off these objects, and so the drone keeps flying. The sound of these drones is different, so you don't hear this high-pitched buzz, but it's more low-frequency sound. So for most people, less intrusive, less disturbing sound. And finally, the whole form of the drone is, has this natural bioinspired feel. So for many people, it's more acceptable to have flying robots that look like birds than not. One other advantage, and that is for future, we can actually make these robots smaller and smaller. We're limited by the technology we have, by batteries, actuators, etc. But the aerodynamics and the flight, the physics allows us to really go smaller, which is not so much the case with a propeller. So like when we think about future applications where we'd like to go as a company, so yeah, we see a lot of opportunities in entertainment, like theme parks with a forest full of flying ferries, but also like more useful applications like robotic guides at airports or a museum where a flying robot will take you to the Mona Lisa painting, or at the airports to the gate where you need to go. And wherever you need to monitor things, whether it's a warehouse or possibly in a greenhouse, and you have people around, you have many obstacles like plants in which you might bump. We think using a wing is better because, again, you can tolerate collisions and you're not harmful to the environment, you're not harmful to people flying there, even if there is some accident. And finally, I talked about the scale at the beginning of the talk, that on Earth we can only fly at, say, hummingbird sizes, but this will be different on different planets, for example. So yeah, it might be an interesting option also for extraterrestrial flight. And as a side note, you may have followed the Curiosity helicopter on Mars that did many flights and was very successful. Eventually, what took it out of service was a hard landing when it hit the ground with its propeller, and it got damaged. Well, with a flapping wing, this wouldn't happen because the wing is just going back and forth, and it doesn't, get damaged that easily when you hit the ground. Just some examples of actually the collision tolerance. These were some tests we did in greenhouses, just in an attempt to see if that would be a good platform for that environment. As you can see, and the flapping wing can tolerate, for example, hitting a plant or flower over here. Doesn't cause much damage, very minor damage, compared to a quadcopter that is just going to chop down these flowers. And what is a very nasty obstacle in these greenhouses are these thin wires, which are very hard to see for us, but also for computer vision. And this is really a killer for propeller-based drones. As soon as the propeller touches it, you're just going down, while the flapping wing can really handle these much better. Okay, there are also some challenges with flapping wings, and they are related to vibrations. I actually didn't include a slide about flight control, but as you can imagine, we get a lot of vibrations in the sensory data, and basically it requires some tuning, some trade-offs between the amount of filtering you do and between the amount of delay you introduce into the control system. But it can be solved, but it is challenging for video. So these days, when you think of drones, it's a flying camera, but we believe that in future it will be more of a flying sensor. But anyway, you will get image blur and image shaking, but with the right settings of the camera, with a better camera, and with some software stabilization, you can get decent images. It's not going to be something for recording videos of your holiday or vacation, but it's good enough for getting information. And there are still ways to improve this, either using global shutter sensors, doing some active stabilization, maybe on the chip level. And finally, what could be quite interesting is use of event cameras, because with these you could actually even get additional information, even from a, let's say, static image. Because of the vibration, you will actually see even static things in the image. Okay, finally, the last kind of challenge I already talked about is miniaturization. So the physics allow us to go really to insect scales. Now, our prototypes, we can make them about half the size and still get 5 minutes flight time per battery. But if you want to go smaller, you start hitting the limits of the motors. We have rotary motors, DC motors. They become very inefficient at very small scales, and that basically prevents flying for longer flight times. So what we need is improvements in, like muscle-like actuators. On the other hand, if you go at small insect scales, you can simplify the design by using compliant mechanisms, which have no backlash. You need less parts, etc. So we see some nice opportunities there once we have actuators for that size. Okay, to end up again with what we do currently. So as I mentioned, the Nimble Plus is the first tailless robot that you can buy. We have multiple purchasing options. You can either get just a base drone, or we also sell a kit with some additional accessories like a remote, like a crazy radio dongle, so you can program it and fly from a computer. We can even configure bundles together with positioning systems. So if this is interesting for you, yeah, please reach out to me. Okay, well, this is it for me. I hope that this was new, possibly new and interesting for you. If you have any questions, I'm here to answer those. Thanks.
All right. Thanks a lot, Matej, for this really interesting presentation. It's always nice to hear the comparison between the Crazy Fly, why you should buy a flapping wing MEV instead. But definitely valid. Yeah, so are there any questions? Just raise your hand or post the question in the chat.
Sorry, I'll just stop the... Yeah, good. So I can see you.
Hey, So I had some questions, but you actually responded to them in your last slides, more about the biggest and smallest sizes, I guess, that you could make with this. So, but yeah, it's really cool to see. I actually didn't know that much. You just found it as like a really cool, interesting platform. Like it's an interesting challenge, but it has a lot of great applications, and I'm really happy to see that you've been doing a lot of efforts into this area. So thank you for the presentation. The only question I guess I still have is, what's the max capacity, like payload-wise, for this type of platform?
So for the current platforms, well, thanks for the nice words, by the way. But for this current platform, which is about 100 grams, and let's say minimum takeoff weight, you can carry extra 30 grams. That is at least what we recommend. But we have customers who are carrying like 60-gram grippers. It will still fly, but of course, yeah, the battery time will be much shorter then.
All right, just quickly follow up. What is the flight time you have right now with the battery capacity?
So with the standard battery, you get up to 8 minutes when you hover, when you have like a fresh, healthy battery. And you can still get about 15% extra when you fly forward because it's more efficient.
Awesome.
With the payload of 30 grams, you will still be above 5 minutes.
All right, thank you.
You're welcome.
Awesome, thanks, Roman. There are 2 hands up, so I'll give the word first. George, go for it.
Yeah, thank you for the presentation. Oh, you can't see me here. Thank you for the presentation, really interesting. So my questions are what a controls engineer would ask. First of all, how many degrees of freedom are there in, well, it's not an aircraft exactly, but UAV, let's say?
I mean, technically it's an aircraft, right? So it's a craft that moves through the air. It has, as let's say quadcopters, it has 4 degrees of freedom that are directly controllable. So it's attitude and basically acceleration in z direction. So thrust. So you get thrust, roll, pitch, and yaw that you can control. We typically operate it in attitude stabilized mode. So you basically give set points to roll, pitch, but in principle you can also do rate control.
And were classic linear controllers good enough for you, or you had to go to some non-linear custom controller?
Yeah, so actually we're using linear controllers, PIDs. I do believe we can get better performance with non-linear controllers, but still, even with a simple PID, you can get pretty good performance already. Yeah.
Excellent. Thanks a lot.
Welcome.
Great, thanks, George. We have a question remaining from Manolo.
Thank you very much for this very interesting presentation. My question is, how are you simulating or modeling the optimal size and material to use for the wings?
Yeah. So in short, we don't. So the whole problem is so complex that we actually don't have good models of this. It doesn't mean that there are no models of, let's say, the wing deformations. So what you would need to do is a fluid structure interaction simulation, because the flow or the pressure distribution around the wing affects the shape of the wing when it's flapping. But this is just too time-consuming. So what we actually do, we approach this experimentally. We have some intuition already. So we use high-speed cameras to observe the wings as they flap to basically see if the shape is good or not, so to say. And we can measure the forces, the thrust forces the wing produces. So this is how we optimize the design.
Okay, and then for the material that you use, so I think with the cameras or the computational fluid dynamics, you could optimize the shape, but I would imagine that, say, silk, for example, would fly quite different to, say, plastic.
Yeah.
And for the actual material for the wings, have you experimented with different material types?
Yes, certainly. So the wing material is very important. So the wings actually that we use now are made of polyethylene foam. But in principle, you need just any lightweight material will do. Any lightweight and reasonably strong material will do. We use the foam because of acoustics, actually, because this material doesn't make much sound when you move it around. But for the, let's say, structural properties of the wings, the shape of the wing is mostly defined by these stiffeners that we place at like certain positions, and this is something that we optimize experimentally. You could, of course, set up a computational fluid dynamics study to do that, but then you need to validate the model, and so it's not that we have never done this. So not me personally, but this is a spin-off of like a university project where we have done a lot of studies like this. But the amount of work you have to put in to get a minor improvement in performance is just too high. So since we're still at the beginning of using flapping wings, you can at this stage make much higher progress just by doing experiments. But certainly, like with CFD, you would get even like you could eventually shave off some additional percentage. I'm pretty sure.
Yeah, it's really awesome. Thank you.
Thanks.
All right, we have another hand from Vignesh. Go for it.
Oh, yes, right. That was an awesome presentation. So I would like to know about, from your experience, the propulsion thrust compared to propeller and the flapping wing, because in propeller you move it horizontally and you get a lift based on the airfoil shape. And since you have a wing right now, so you have to, I'm not sure what the shape of the wing, but you have to constantly flap it to get the upward propulsion thrust. So I would like to, so for me, yes, like this platform suited for different applications when compared to propeller-based drones, but I would like to know the propulsion thrust comparison between both the platforms.
So you're interested in the difference in, let's say, propulsion efficiency of yes. Propeller and a wing? So yeah, I actually had one slide that kind of addressed this. It is still an open question, to be honest. Like, is a flapping wing better than a propeller or not? But at least with our platform, we show that you can get comparable efficiencies with a flapping wing, like you would do with a propeller, at least at the scale of let's say 100 grams. So at this scale. So with our wing, we can lift. Using 1 watt of power, we can lift about 6 to 7 grams. Okay. If you like, for example, look into like motor specifications for FPV drones, very often you will get numbers like 3 grams per watt. But this is because there you just need the high thrust, and you don't care that much about efficiency. For very large motor propeller combinations, you can get even 20 grams per watt, but it is at much larger scale where the motors are more efficient. So yeah, like we're not the best, but I would say we're comparable to propeller-based drones at the scale at which the flapper drones are currently.
Yeah. So I actually joined it late, so I couldn't see all of your slides, so probably I missed it. But from what, yeah, I get it. And I would like to know the cost of your platform, just a rough estimate of how much does it cost, one thing, and do we have any open source simulation platform to try it out?
Yeah. So the cost, our platforms, they start at 1,500 euro, so about $1,550 US, I think. What you get is a development platform. So indeed, like the software is open source. We provide any parts as spares if you need. So it's a product with long product support. It's not like a drone that next year you cannot maintain anymore. To your second question, there is no readily available simulator that you could use. That said, there are now some attempts to simulate the crazy flies, and it is interesting because the control loops are pretty much the same, and the physics of flight are of course slightly different. We don't have, let's say, ready to share models, but there are some scientific papers that we can recommend to use as a base if you would like to create your own model. But it's also something many users are asking us, and well, we're a small team, so we cannot really do all of that ourselves, but we hope that within the community, we will create models that will then be shareable with others.
Yeah. Thanks a lot. Those, thank you. Thank you.
All right. Thanks, Vinesh, for your great questions. I'll just double check. I think Archie, he had some questions about like, yeah, which software do you use for simulation of platform? I guess that has already been answered. There is currently none readily available, but ours happens to be from the simulation subcommittee, so that is perhaps something that, yeah, let's see, maybe in the future we can help out with. But Arch, do you have any other questions since yours was already answered in the chat? Perfect. All right. Well, of course, like if you have any more questions, you can always post them in the Discourse post where this presentation was announced, or yeah, put them in Discord, or they ask them to Matej himself, because he, of course, also shared his contact information as well. So then it's time to wrap it up a bit. So let me try to share my slides, or find my slides again. One moment, because I think I've closed them again. That wasn't handy. Yeah. All right. I think I found them. All right, I'm just going to end also with a kind of a reminder for the subcommittees that we have a developer meeting in 2 weeks. So there's like, we kind of came to a conclusion of what kind of recommended environment we want to develop in, which Ubuntu 2204 was too humble, and Gazebo Harmonic. Even though that's not the recommended combination, that is the preferred simulator. At least what we heard from the Autopilot team, and I think the PS4 team as well. So that's kind of like what we came to the conclusion last time. For indoor navigation, my young is currently continuing to try out AeroStack 2. There's an issue open for that, so if you would like to try it out yourself and have some feedback, go for it. And I guess for the simulation subcommittee, we still need to determine if a good simulator environment vehicles we need for people to develop in. I haven't seen an issue or discussion created so far, but we can do that in the next 2 weeks. And documentation, well, we've kind of like released the website so far, so we're currently working also on a contributing guides to, once we release it a little bit more to the public, that they will have more instructions to append to the aero robotic landscape. And yeah, because we're all developers, we all know how to make pull requests, but not everybody does. So yeah, so those are just the last words. So the next up is like I said, a developer meeting is on the 5th of June, also 4 p.m. UTC. Yeah, and then this is the URL for the aero robotic landscape and information if it's missing. Yeah, and also kind of like, you know, our main watering hole is github.com/Ross Ariel. So yeah, that's it for now. Thanks a lot for joining. Thank you again, Matej, for your great presentation, and we'll see each other again in 2 weeks. Thank you.
Thank you, Kim. Bye-bye.
Thanks for having me. Bye-bye.